So yesterday we saw how we differentiate logarithmic functions. Now, integrating log functions, that's a 4-unit thing. And we'll see how we do that later on when we look at integration techniques for extension 2. So basically it's the reverse. What we look at now anyway is the reverse of yesterday. And remember, when we differentiated a log, we ended up with derivative on function. So logically, if I have a situation where I've got derivative on function and I'm going back the other way, it must have come from a log function. So if I integrate derivative on function, I get the log of function x. Plus, of course, a constant. All right, so we see something like this. Now, how do I know it's going to be a log situation? I guess the first technique I'd try, if I didn't realise it, would be to put it into index form. And if we put that into index form, it's going to be to the power of -1. But we're going to add 1 to the power over the power. Well, if you add 1 to -1, you get 0. And you can't put 0 on the bottom of the fraction. So if you get that situation, you go, oh, something else is happening here. This can't be just a straight add 1 to the power over the power. So can we create the derivative? Well, the derivative is -3. So I'll make the top -3, but I can't just change the question. So to balance it out, I'll multiply it by -1/3 out the front. The integral now is derivative on function, so I know that will go to the log of the function. So we get -1/3 the log of 7 minus 3x. So same idea. If I was to try and do this in index form, a power of -1, oh, add 1 to the power, I get 0. No good. Can I create the derivative on top? Well, the derivative is 8. So I'll multiply the top by 8, but to balance it out, I'll need an 8th out the front. And that'll be an 8th of the log of 8x plus 5. And remember, these are all natural logs when we do this. The base does matter. Okay. In this case, the derivative would be 6x to the power of 5. When you're looking at polynomials, the other thing to watch out for, if the degree of the polynomial on top is 1 less than the degree on the bottom, then again you're going to have a log function. Because when you differentiate, you subtract 1 from the power. So when I differentiate the x to the 6, I would get 6x to the power of 5. So let's balance that one out. We'll make it 6x to the power of 5. Multiply by a 6 out the front, and we get a 6th the log of x to the power of 6 minus 2. Here's an interesting question. The integral of 1 over 5x. Okay. Well, I'll make it the derivative on top. The derivative of 5x is 5. Balance it out. I get a 5th. So the answer is a 5th log of 5x plus a constant. What if I'd done this another way? Because remember, we can factorise constants. So I've factorised the 5th out of the front of the integral. Integrate 1 on x, I get log x plus a constant. Different answers. Or are they? They are actually the same answer. Why? Yeah, it's all to do with the constant. Whilst I put plus c on both of these, they're actually different constants. I could keep going with that 1/5 log of 5x. I could go, well, 1/5 of log of 5x plus a constant. I could use my log laws on the log of 5x and go, oh, well, that's 1/5 the log of 5 plus 1/5 the log of x plus a constant. Well, a 5th log 5 is a constant number. So it's different to the constant that I got over here, but it's still a 5th log x plus a constant. Now you don't have to make it a 5th log x. That's a perfectly fine answer, the 5th log 5x. 4x plus 1 on 2x plus 1. I said before, we can create the derivative on top. Now, 4x is too much. I want the power to be 1 less. Whenever you see these algebraic fractions, if the order of the polynomial on the top is the same or more, so this case is the same, they're both of degree 1, do a polynomial division first. So 4x plus 1 over 2x plus 1 And if you're unsure, I've done my division over there, but it turns out to be 2 minus 1 on 2x plus 1. And then we integrate each individual bit. Integrate the 2, we get 2x. Integrate the minus 1 on 2x plus 1, we'll get minus a half log 2x plus 1. So, order of numerator greater than or equal to denominator, polynomial division. Let's do a definite one. Derivative's already on top. We don't have to do anything for this one because the derivative of x squared plus 1 is, of course, 2x. So it's the log of x squared plus 1. Substitute in 2. Substitute in 1. Log 5 minus log 2. Log 5 on 2. Now, some people go straight to log 5 on 2 because they know that I'm going to subtract logs, and the log laws say when I subtract I do a division. So they go log, substitute in the top, that goes to the top of the fraction, substitute in the bottom, that goes to the bottom of the fraction. So it is possible to jump straight from there to log of 5 on 2. Thank you. Questions like this. Basically they're giving me a huge hint that x squared log x, if I were going to integrate it, it's going to have something to do with x cubed log x. But they're helping us out by saying, hey, go and differentiate this first and see if you can see the pattern. Well, if I differentiate it, got to use a product rule. Write down the first, diff the second, plus write down the second, diff the first. There's that x squared log x we were expecting. Now, what does that mean? It means that when I differentiate x cubed log x, I get x squared plus 3x squared log x. Therefore, when I integrate x squared plus 3x squared log x, I should get x cubed log x. That's where I'm going to start. Now, our rules for integration say I can break that up and integrate each term individually. So I could rewrite this whole expression as 3 lots of the integral of x squared log x. I'll move the integral of x squared dx to the other side. And also on the other side we have the x cubed log x and the constant. So integrate the x squared and I get 1/3 x cubed, but we're going to divide both sides by 3 as well. And we come up with the integral that they're looking for. Remember, sometimes we don't think of these things as equations, but this is an equation. We're saying this derivative equals that. So the rules of equations apply. Whatever you do to one side, you do to the other. And that's what I've really done here. I've just integrated both sides of the equation. And then I've moved terms, just like we do with equations. There's our last questions to look at for the year. Well, other than, of course, the reviews, which keep up to date with those over the holidays. Get a taste for it, get ready for a big year.